Hello, I'm Mr. Beck from War Hill High School, and this is your introduction to Lewis dot structures. The objectives of this lesson will be for you to recognize that ionic compounds are going to form in order to meet the octet rule by transferring electrons. So elements will transfer electrons from one to another in order that they meet the octet rule. For molecular compounds, we're going to see that the elements are going to share electrons in order to meet the octet rule. We also are going to recognize that hydrogen is going to meet its octet rule by looking like helium. That's what isoelectronic is going to mean. It's going to have the same number of electrons as helium in order to obey its version of the octet rule. And then we're going to recognize that in a Lewis structure, when we look at the lines, each line in that Lewis structure is going to represent 2 electrons. The way we're going to get to this understanding to meet these objectives is we're going to take the following steps. First, we're going to review the Bohr model of the atom and identify what valence electrons are. Second, we're going to define the octet rule and what it means for various atoms. Next, we're going to show how the elements are going to form ions if they're in an ionic compound in order to satisfy the octet rule. And that way we will be able to identify common charges of elements within the periodic table. We're going to show how ionic compounds are going to satisfy the octet rule when various metals and nonmetals get together. And then we're going to show how molecular compounds are going to satisfy the octet rule with single, double, and triple bonds as those elements share electrons in order to form molecules. So let's start with a review of the Bohr model of the atom. In the Bohr model, Niels Bohr showed us that electrons can exist in specific energy levels as they travel around the nucleus. We call these energy levels shells or orbitals, and we usually label them with the lowercase n, n equals 1, 2, 3, 4, 5, 6, around the central positive nucleus. Now, each orbit, each shell or energy level is going to include electrons, and those electrons, when they absorb energy, they're going to jump from a lower energy level up to a higher energy level. And if then they release that energy, they're going to drop from a higher energy to a lower energy. And they're going to release that energy in the form of light. This Bohr model helped us understand atomic spectra because as the electrons drop from different energy levels to other energy levels, they're going to release specific amounts of light, specific photons with very specific energies. And those photons show up as different colors of light. So when we look at the atomic spectrum of hydrogen, we can see that this purple line happens when it jumps from orbit 6 to 2. If it jumps from 5 to 2, we get a different colored line. From 4 to 2, we get this teal sort of line, and orbits 3 to 2, we get a sharp red line, actually. So those are from the hydrogen spectrum, and the Bohr model helped us understand the spectrum. But what's important for us now is just knowing that those energy levels exist in order to understand Lewis structures. So with the energy levels, we're going to have rules for where the electrons exist. And these rules work up through calcium. Beyond calcium, atomic number 20, we get some interesting exceptions to these rules. So first, that first orbital, that n equals 1, can hold a maximum of 2 electrons. And if we look at the periodic table and we look at the first row of the periodic table, we see that there are 2 elements, hydrogen and helium, that exist in that row. And so the periodic table is going to match some of these rules for where electrons sit. The second orbit and the third orbital will hold a maximum of 8 electrons. And again, if we look at the periodic table for n equals 2 and n equals 3, the second and the third row, we can count 1, 2, 3, 4, 5, 6, 7, 8 elements across that level and 8 elements across the next level. So each row can correspond up until calcium. Each row corresponds with the number of electrons that will fit in that shell. It does get more complicated as we move forward, but we're going to use these rules so far up to calcium. And so again, n is known as the energy level or the principal energy level for that. So the numbers 2, 8, 8 are going to be important to us. And the electrons that are occupying the outermost shell are what we're going to call valence electrons. So let's take a couple examples of how these electrons exist within atoms. Let's take a look at lithium, sodium, and potassium. If you look at the periodic table, you'll see that these are in the first column of the periodic table, or the first group. So lithium is atomic number 3 and contains 3 protons. In order to have a neutral atom, lithium also must include 3 electrons. So, well, if we're placing the electrons in the orbitals, the first level is going to hold 2 electrons, so we fill in those 2 electrons first. And then we have 1 more electron to make a total of 3, and so that next electron can't fit in the n equals 1. That next electron is going to go into n equals 2. And so lithium will have 2 electrons in the first level and 1 electron in that second level. So lithium has 1 electron in its outer shell. Sodium has 11 protons, and therefore it's going to have 11 electrons in order to be a neutral atom. So the first 2 of those 11 electrons are going to go in the n equals 1 in the first shell. The second shell can hold up to 8, so if I placed 8 electrons in the second shell, now I have 8 plus 2 is 10. So sodium has 1 more electron. We're going to place that electron in the third shell. So now we see sodium has 1 electron in its outer shell. If we look at potassium, potassium has 19 protons, so it has 19 electrons. Let's place 2 electrons in the first shell. Then we have another 8 electrons that'll fit in the second shell for a total of 10, 8 plus 2. Now that leaves me 9 more electrons, so we can place 8 in the third energy level, so that's 2, 8, 8, and that is a total of 18 electrons. And that's 1 more electron, and let me place that 1 electron in the fourth shell. So now we see that lithium has 1 valence electron, 1 electron in its outer shell. Sodium has 1 electron in its outer shell. Potassium has 1 electron in its outer shell. And so the number of electrons in the outer energy level, the outer shell, is going to be the same within each group, within each column of the periodic table. So that first column, all the atoms are going to have 1 electron in its outer shell. We call that outer shell the valence shell, and the electrons that are in that outer shell are going to be valence electrons. So that we see everything in that first column is going to have 1 valence electron. Column 1 will have 1 valence electron. If we take a look at all of the first 20 atoms, and here I've represented the shells just with curves, and the electrons are represented by X's in this representation. Hydrogen has 1 proton, so it has 1 electron, and I've placed that electron in the first level. Helium has 2 protons, and it therefore has 2 electrons, and so I've placed those 2 electrons in the first level. Lithium has 3, but I can't place a third electron in the first level because it only holds 2. So lithium gets its first electron in the second level. And so you see that hydrogen has 1 electron in its outer shell. Lithium has 1 electron in its outer shell. If I continue along through beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, we see we get 2, 3, 4, 5, 6, 7, and finally 8 electrons in neon's outer shell. No more electrons will fit. So that's why the periodic table returns back to the first column, so that I could place that 11th electron for sodium out again in a new shell, out in the outer shell. The same thing happens as I go from sodium all the way to argon. For argon, I get 8 electrons in that outer shell, and therefore no more will fit. So I have to go to potassium. I have to add a new level and get a new electron in that outer level. But what you see in this picture, if this represents groups 1, 2, 13, 14, 15, 16, 17, and 18, we see that the group number is going to help us figure out how many valence electrons. That whole first column, group 1, is going to have 1 valence electron. Group 2, of course, has 2 valence electrons. Group 13, if we just look at the 3, is going to have 3 valence electrons, and so on with 14, 15, and 16. If I look at the 4, 5, and the 6, then I have 4, 5, and 6 valence electrons. Group 17 has 7 valence electrons, and group 18 has 8 valence electrons, except, of course, for helium, which can only hold 2 in its outer shell. So helium has 2 valence electrons. If we look at the periodic table overall, we can predict the number of valence electrons by which column the atoms are in. So group 1 has 1, group 2 has 2, 3, 4, 5, 6, 7, and 8. Oh, wait a second. We had to move helium over to the left because helium can only have 2 valence electrons. So the first shell only holds 2 electrons. So even though helium normally exists over to the right in column 18, it's going to have only 2 valence electrons because only 2 will fit. And you might ask, what about all the yellow ones? Well, those are very strange and unpredictable, so we can't predict from the periodic table how many valence electrons those have. So now that we know for many of the elements how many valence electrons electrons they have, we can show what we call a Lewis dot structure, and the Lewis dot structure will show only the valence electrons. We're going to represent each electron with a dot and place it around the element symbol. So we start with the element symbol. I just wrote X for an example element symbol, and that's going to represent all the electrons that are not in the outer shell. So we can think of that as the core electrons. And then we imagine that there are 4 locations around that element into which we can put the electrons, because we must understand that electrons eventually will show up as pairs. So if we think of this as 4 places, which will hold up to 2 electrons each, that'll be a total of 8 electrons that we hold as 4 pairs of electrons around that atom. And then the electrons are going to spread out as I add them before doubling up. So I don't want to fill in one of these boxes before I've spread the electrons around to the other boxes. There are exceptions to this with hydrogen, helium, lithium, and beryllium, but otherwise we're generally going to be spreading the electrons out before doubling them up. So let's take a look at some examples. Let's take an example of an element in group 1. Let's take a look at sodium. If you look at the periodic table, sodium is element number 11. It has 11 electrons total, but if we put 2 in the first level and then 8 in the second level, that's 10 electrons. That leaves 1 valence electron. So we know since it's in group 1, we really only have to worry about that 1 valence electron. And so we can place that electron in any one of those 4 boxes. I tend to place it to the right, but it would be perfectly fine to place it on the top or the bottom or the left. If we take a look at element magnesium, magnesium is in the second column. It has 2 valence electrons. And so I don't want to double them up. I want to spread them out before doubling up. So I put 1 on the right and 1 up top. It's okay if you chose 2 different locations. For column 13, group 13, let's pick aluminum. Aluminum, since it's in column 13, in group 13, it's going to have 3 valence electrons. And again, we're going to want to spread those out before doubling them up. So I placed 1 on the right, 1 on the top, 1 on the left. Next, we can get to group 14. It is silicon we're going to use as an example. Since it's in group 14, it has 4 valence electrons. And so we're going to spread those out, 1 on the top, 1 on the right, 1 on the left, 1 on the bottom. Group 15 is going to have 5 valence electrons. So let's look at phosphorus. With 5 valence electrons, we can only spread them out so much before we have to start doubling them up. So we'll find that with 5, I have 1 on the right, 1 on the top, 1 on the left. And now I'm going to place 2 on the bottom, because I need something doubled up because I don't have any more places to put them. So phosphorus has a pair of electrons and then 3 lone electrons. Group 16, we can have sulfur. That's going to have 6 valence electrons. So you see if I go left, right, top, bottom, I would have 2 more. So I'm going to have to double up in 2 places. So what I've done is I've doubled up on the right and doubled up on the bottom, and then a lone electron on the left and a lone electron on the top. Group 17, we could have chlorine. Chlorine is going to have 7 of its 8 possible electrons. So I can spread them out and then start doubling them up. And I'll wind up with a pair on the top, a pair on the left, a pair on the right, and then a single electron off to the right there. Now you see that you could have had the single electron on the top or the bottom or the left or the right. Doesn't matter as long as you have one place with a sole electron. And then finally we get to group 18. Let's pick argon. And argon has 8 valence electrons since it's in group 18. And so therefore argon is going to have pair, 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 pair on the top, bottom, left, and right. So this is how we have the Lewis dot structures of elements showing only the valence electrons. The octet rule applies to all elements, and it says that atoms are going to tend to gain, lose, or share electrons to obtain a full outer shell. So this number 8, since we have 8 places for electrons around the atom, all atoms are going to want to have that full outer shell, or typically 8 electrons. What we see is that the noble gases, they already have their full outer shell, so they're stable. They're not going to gain, lose, or share electrons. They're very non-reactive. If we take a look at the nonmetals tend to gain or share electrons, and hydrogen is often going to behave like a nonmetal, so I slid it over from the left and attached it with the nonmetals. And then the metals tend to gain electrons when they form compounds. Sorry, the metals tend to lose electrons when they form compounds, so the metals are going to become positive as they lose their electrons. Now the octet rule, of course, atoms will gain, lose, or share electrons to obtain a full outer shell. And so for most atoms, that's going to be 8 electrons, or what we call an octet. Again, if you look at the noble gases, they are very stable. They have a full outer shell, and all the other atoms want to wind up looking like one of the noble gases when they get to their final, when they're in a compound of some sort. So all atoms are going to want to look like the noble gases. Of course, hydrogen, lithium, and beryllium are close to helium on the periodic table, so they are going to wind up looking like helium as they gain or lose electrons. So those are exceptions to the octet rule, or hydrogen, lithium, and beryllium. They're only going to want 2 electrons. So let's take a look at some examples of how elements will obtain the octet using the octet rule. Chlorine is in group 17, therefore it has 7 valence electrons, which I've drawn. What chlorine really wants is 8 valence electrons. It wants to fill that octet. So if chlorine were to add 1 electron from somewhere, we'll worry about where later. If chlorine were to add 1 negative electron, what that would mean is that it would have its octet full, but then it would have a charge of -1. Because now this was a neutral chlorine atom with 7 valence electrons. And if we added 1 more electron, then all of a sudden we have a -1 charge. So adding an electron gives me a negative charge because electrons are negative. But now chlorine has satisfied the octet rule and it has a charge of -1. Let's take a look at nitrogen. Nitrogen is in group 15, so it has 5 valence electrons, which I've drawn as 2, 1, 1, and 1. In order for it to fill its octet rule, in order for it to fill its outer shell, it's going to have to add 3 electrons from somewhere. So if nitrogen then were to have 3 more electrons, that would give it a full outer shell and it would have a charge of -3. So nitrogen adding 3 electrons gets a charge of -3. If we take a look at lithium, lithium has a single valence electron. Lithium could either gain 7 electrons to get a full outer shell, or it could lose 1 electron. That's why metals tend to lose electrons. Lithium is a metal. It's going to try to lose that electron. So if it loses the electron, does that mean it has nothing? Well, if you take a look at the Bohr model of lithium, what we see is that it has 3 protons. It has 3 electrons, 2 in the first level, 1 in the second level. So if it loses that outer electron, then what we see is it becomes lithium with a +1 charge, but now its inner shell has now become its outer shell. Since there are no electrons in that outermost shell anymore, then the inner shell is now its outer shell, and that shell, the first shell, is full. So now lithium has achieved a full outer shell by losing its outer shell. So its inner shell was full, and now that full shell is now its outer shell. So lithium now has satisfied the octet rule because lithium looks like helium as far as number of electrons. If we take a look at magnesium, magnesium also is a metal. It has 2 electrons. It could either gain 6 or lose the 2. Since it's a metal, it's going to tend to lose the electrons. So again, if we look at the if we look at the Bohr model of magnesium, we see it's got 12 protons, so it would have 12 electrons, 2, 8, and 2. If it lost those 2 electrons in the outer shell, those are the ones that showed up in the dot structure, then we wind up with magnesium having a +2 charge because its inner shell is now full. Magnesium is happy because it is going to have its full outer shell. It's actually going to be looking like neon with 10 electrons. So this would be the electron structure of neon on the bottom. So that's what happens, is that, again, we have a full outer shell because the inner shell is now its outer shell. So magnesium is happy in terms of valence electrons. In order to form ionic compounds, now that we know about how atoms want to gain or lose electrons if they're going to meet up, now we're going to show where those electrons come from. So nonmetals, when I have an ionic compound, they're going to form between nonmetals and metals. And so the nonmetals are going to gain electrons while the metals lose electrons. So if they get together, some can gain and some to lose in order to meet the octet rule. So if we look at LiCl, lithium chloride, lithium is a metal and it has 1 valence electron. Chlorine is a nonmetal, it has 7 valence electrons. Chlorine wants 1, lithium wants to get rid of 1. So this is a match made in heaven. If lithium were to transfer its lone valence electron to chlorine, what we'd wind up with is a lithium with a +1 charge, a chlorine with a -1 charge, and overall that compound is going to be neutral because I have a +1 and a -1. And the +1 is going to be attracted by the -1, and they're going to stick together and form an ionic compound, lithium chloride. So we see that that transfer of that one electron created the charges, and overall the compound was neutral. If we take a look at CaF2, we see calcium has two valence electrons. It's in the second column. Fluorine is in the 17th column, or group 17. So it's going to have seven valence electrons. And now calcium wants to lose two, and each fluorine wants to gain one. So if calcium could transfer its two electrons, its two valence electrons, to the two fluorines, what that's going to lead to is a calcium plus 2 ion, and then two fluorine minus 1 ions. Again, overall, you're going to see that that compound is going to be electrically neutral with a plus 2 and two minus 1s. But this is done by transferring valence electrons so that each atom becomes charged, a charged ion, and then those ions attract in a ratio such that they wind up balancing out the charge. Let's take a look at magnesium oxide. In this case, magnesium is in the second column. It has two valence electrons. Oxygen is in group 16. It's going to have six valence electrons. Oxygen wants two, magnesium wants to get rid of two. So magnesium can transfer its two electrons to the oxygen. That would produce a magnesium plus 2 ion and an oxygen minus 2 ion. And those, again, would be electrically neutral. When I put those two ions together, the plus 2 and the minus 2 would electrically cancel out, and so I would wind up with a neutral compound. If I take a look at three lithiums and a phosphorus, lithium phosphide, then each lithium wants to get rid of one electron because lithium has one valence electron and it's a metal. Phosphorus is in group 15. It has five valence electrons. It wants to gain three electrons. So if we match these up, three lithiums to one phosphorus, we can see that the lithium each would lose one electron to the phosphorus, and the phosphorus would gain a total of three electrons. That would give me three positive one lithium ions and a single negative 3 phosphorus ion. So those, again, would combine the minus 3 with the 3 plus 1s, and that would form a neutral compound. So you can see everyone is meeting the octet rule, and we have compounds that are winding up neutral afterwards. So this is how ionic compounds are going to form. With molecular compounds, those are made of nonmetals, and the nonmetals are going to share electrons in order to meet the octet rule. So for example, if I take H2, then hydrogen has one valence electron in its shell, and it only has one electron. And that shell, that first shell, can only hold two electrons. So hydrogen really wants to have two electrons. So if I have two hydrogens together, each with one electron, and they were to decide to share that pair of electrons, then the hydrogens can join together and form an H2 molecule. Now, the hydrogen on the left thinks that it has a pair of electrons. The hydrogen on the right thinks that it has a pair of electrons. So each hydrogen has met the octet rule, and that's going to form H2. And we see that we can replace that pair of electrons with a single line to represent a shared pair of electrons. So the single line represents a shared pair. If we take a look at F2, each fluorine has 7 valence electrons. Each fluorine wants 8. But if fluorine were to share that pair of electrons, then what we're going to get is each fluorine obeying the octet rule by sharing that pair. So the fluorine on the left thinks it has a full octet, the fluorine on the right thinks it has a full octet, and both fluorine atoms are happy because they have their full octet. We could replace that pair of shared electrons with a single line, just like we did before. So that line, that single line, represents two electrons. And now we notice we have these extra pairs of electrons on the outside. We have to know that those electrons that are not involved in bonds are called lone pairs. So electrons not involved in bonds are known as lone pairs of electrons. We can now look at the example of water, H2O. Each hydrogen brings one electron with it. The oxygen brings a total of 6 electrons. Now everybody wants a full outer shell. The hydrogen wants 2, the oxygen wants 8. So if they were to get together and share that pair of electrons with the hydrogen and the other pair of electrons with the other hydrogen, then what we wind up with is oxygen having a full octet and each hydrogen having its full outer shell of 2 electrons because it's going to look like helium. And then hydrogen each thinks it's happy, oxygen thinks it's happy, and what we have is everybody satisfying the octet rule. Now again, we can draw those pairs of electrons as single lines. So this is what we get with H2O, and oxygen is going to have 2 lone pairs attached to it. So note the 2 lone pairs. The The electrons not involved in bonding are the lone pairs of electrons around oxygen. Let's finally look at O2, or let's next look at O2. Oxygen, if we share this pair of electrons and that pair of electrons, now oxygen each brings 6 to the table, and if they share 2 pairs of electrons, then what we wind up with is that each oxygen thinks it has a total of 8 electrons. So I've got that shared pair in the middle, the shared 2 pairs in the middle, and each oxygen is claiming that shared pair for a total of 8 electrons around each oxygen. Now what we're going to do is we're going to draw those 2 shared pairs as 2 lines, each line representing 2 electrons, and that gives me a double bond, 2 shared pairs, or a double bond. Now let's take a look at N2, so 2 nitrogen atoms coming together. Nitrogen is in group 15, has 5 valence electrons, and so with 2 nitrogens, if we can share 3 different pairs, we share the pair on the top, the pair on the middle, and the pair on the bottom, that's 3 shared pairs of electrons. That way, each nitrogen is thinking it has a full 8 electrons by sharing those 3 pairs. So nitrogen on the left with 8, nitrogen on the right with 8. With 3 pairs, what we're going to wind up is drawing 3 lines between those nitrogens. Again, each line represents 2 electrons. So you take a look at the nitrogen on the left, it's got a lone pair and then 2, 4, 6 more electrons for a total of 8 electrons. Same with the nitrogen on the right. So both of these nitrogens are satisfying the octet rule by sharing the electrons. Now notice those 3 lines are going to represent 3 shared pairs, or what we call a triple bond. So each line is 2 electrons. Now let's take a look back at the objectives we had for this lesson. We wanted to recognize that ionic compounds are going to form to meet the octet rule by transferring electrons. We showed that. We also showed that molecular compounds are going to meet the octet rule by sharing pairs of electrons. We know that hydrogen is going to meet the octet rule by being isoelectronic with helium. That means it's going to have 2 electrons. That's what isoelectronic means, is looking like. So the same electron structure as helium with 2 electrons instead of 8. And then we also needed to know that each line in a molecular compound that we draw is going to represent 2 electrons. So we saw that with single, double, and triple bonds. I hope this was useful for you, and come back and look for the next presentation where we are going to apply drawing Lewis structures to more complex molecules.